By definition, a circle is the locus of all points equidistant from some given point called the center. So if this dot here represents the center, then the locus of all points equidistant from this dot here will be a circle. Okay, so our center is somewhere here. Okay, now the common distance r from the center to the point on the circle is called the radius of the circle. So for example, this distance here, if we call it r, will be the radius of our circle. Now if you take let's say any line segment joining 2 points, so I have these 2 points here, P, let's say, and Q. Any line segment joining these 2 points is called a chord. So a chord is any line segment joining 2 points of a circle. And clearly a diameter is an example of a chord, right? Because diameter is a special chord which is passing through the center of the circle. The first results of our lesson states the following. Given 3 arbitrary points, say A, B, and C, which are not collinear, meaning that they don't fall, all 3 of them do not fall on one single line, there is exactly one circle passing through those 3 points. All right, let's try to justify this claim. So we consider 3 non-collinear points, A, B, and C. Now we'll let B be a perpendicular bisector of AB. So this line here is B. And then we'll let C be a perpendicular bisector of the segment line AC. So in other words, we have this and this go to each other. All right, so because AB and AC are not parallel lines, they're not also the same lines, then BC, let me call, I forgot to label it C, must actually, the 2 lines B and C must actually meet at a point which we'll call P. Okay, so let B be the perpendicular bisector of AB, and we let C be the perpendicular bisector of AC, and we let P be a point at the intersection of B and C. Now, clearly, PA, right, must be equal to PB from a result that we've seen earlier, we've actually shown earlier, which states that the points on the perpendicular bisector of a segment line must be equidistant to the endpoints of the segment lines, right? So in other words, what we have here is that PA must equal to PB, and using a similar reasoning, we must also have that PA must be equal to PC. So they're all equal to each other, right? Next, let R be the distance PA, which is the same as PB, which is the same as PC. And let gamma be a circle centered at P, okay, with radius R. Then gamma passes through point A, B, C. Like that. And this is exactly what we want. Let us now introduce some new terminologies. First, given a triangle ABC, since the vertices A, B, and C are non-collinear points, then there exists a unit circle which is passing through them. We have just shown that. This unit circle which is passing through the vertices is called the circumcircle of the triangle. And in that case, we'll say that the triangle ABC is inscribed in the circle. Okay, this concept can be generalized to polygons. So that means shapes with more than 3 vertices. So it could be a quadrilateral, you know, a 5-gon, 6-gon, whatever. In any case, if you have a polygon, all of whose vertices lie on a circle, we shall say that this polygon is inscribed in the circle. Next, 2 points A and B on a circle divide the circle into 2 pieces, each of which is called an arc, denoted AB. Okay, so if we consider this circle here, then there are 2 arcs that you can see. You can see this arc here, and then the red part also is an arc. So this is a little bit ambiguous, right? Because there, when we write the notation arc AB is ambiguous because it's not clear whether it's the blue one or the red one. Very often the arc denotes the smaller one. But it may be actually be better, in case there is a possibility for confusion, to introduce a point in between, let's say A and B on this side. Let's call it C, and then let's introduce another point here which we call D. So the blue arc here will then be ACB, and then the red arc could be denoted ADB to avoid confusion. But very often it should be clear from the context which part of the arc we are actually talking about. Now, given an arc AB on a circle which is centered at O, the angle AOB is called the central angle corresponding to the arc. And very often we will measure an arc by its central angle in degree. Okay, also keep in mind that the size description of an arc only makes sense to the circle of which it is a part. Our next result says that an inscribed angle in a circle is equal in degrees to 1/2 of its subtended arc. Let me explain what this means. There are exactly 3 cases to consider. In the first case, let's suppose that angle APB is inscribed in a circle centered at O. Then it's possible that the side PB contains the center of the circle. That's the first case. And what the result says is that the angle APB will be exactly 1/2 of the measurement of the arc AB, which subtends the angle at P. So to prove this case, we will actually appeal to Pythagorean theorem. So by Pythagorean theorem, let me draw this side here. If we consider in triangle, the triangle OAP is an isosceles triangle, right? Because OA is equal to OP and they're both equal to the radius of of the circle. So this should be since. Then it must be the case that angle A is equal to angle at P. So by Pythagorean Theorem, since angle OAP is since the triangle OAP is an isosceles triangle, then angle A must be equal to this angle here at P. Now, angle AOB, what is the angle AOB? This angle here, let me okay, the angle AOB is exterior, right, to the triangle AOP. Okay, and as such, angle AOB must be equal to the sum of the remote angle A and P, which are all equal to each other. Thus, angle at P is 1/2 of angle AOB, right? But this angle here corresponds to the arc AB. Right. Okay, so the angle, so we have proved that the angle APB is 1/2 of the measurements of the arc it subtends, but the arc it subtends has a measurement of an angle of AOB degree. So we get that APB is equal to 1/2 of the arc AB as desired. But that's just one case. For the second case, you can see that the center of the circle is actually inside the angle APB. And from the previous result, we know that angle APQ, this angle here, is going to be equal to 1/2 of the arc AQ, right? So that'll be 1/2 of the measurement of arc AQ. And we know that angle QPB this angle here is going to be 1/2 of the arc QB. On the other hand, we know that angle APB is the sum of angle APQ and that of angle QPB. So this will be 1/2 of the measurements of AQ plus 1/2 of the measurement of QB. And of course, we can factor the 1/2 out. So now if you were to add, so we have now AQ plus QB, that's precisely, so the angle which subtends this arc is the angle AOB, right? So we can then now say that angle APB is 1/2 of the measurements of the arc AB as desired. Now for our third and last case, the center O is actually outside of the angle APB, but that's not a problem because we know that APQ, the measurement of APQ, is 1/2 of AQ. And we know that the measurements of BPQ is 1/2 of BQ. Now angle BPA is angle BPQ minus angle APQ, which is then 1/2 of BQ minus 1/2 of AQ, which is going to be then 1/2 of AB. So in all three cases, we get exactly the stated result, which is remind you is the following: an inscribed angle in a circle is equal in degrees to 1/2 its subtended arc. All right, so a direct consequence of the result that we just proved states that opposite angles of an inscribed quadrilateral are supplementary, meaning that they add up to 180 degrees. So to prove this result, let's consider a circle here drawn in red, centered at O, and suppose that ABCD is a quadrilateral which is inscribed in the circle. Okay, now note that angle ABC is 1/2 of arc ADC. Right, so ABC is this angle, and the arc ADC is this arc. All right, so it subtends the angle ABC, subtend the arc ADC, and from what we've seen earlier, will be 1/2 of its measurement. So similarly, angle ADC is going to be 1/2 ABC, and feel free to pause the video to double check. As such, angle ABC plus angle ADC is going to be equal to 1/2 ADC plus 1/2 ABC, which is then 1/2 ADC plus, yes, so that would be 1/2. Now if you take ADC and then you add that up to ABC, right, you get the full circle. So this will be exactly 360 degrees, and 1/2 of 360 degrees is 180 degrees. So if we add ABC to ADC, which are opposites inside the quadrilateral, then we get exactly 180 degrees. And there's nothing special for about the choice of the angles used for our proof here. So you can play the same game for A and C, or any arbitrary opposite angles inside an inscribed quadrilateral. Another corollary of the theorem that we proved earlier is the following: the angle between two secants drawn to a circle from an exterior point is equal in degrees to 1/2 the difference of the subtended arcs. Let me try to substantiate this a little bit. So suppose you have this circle here, which is being shown here, and then I have an exterior point X, and I have 2 points A and B on the circle. So AX and BX are secants. Drawn to the circle. Okay, Now consider the arcs AB and this arc here, let's say UP. This result says that the measurement of AXB, which is this angle here, the measurement of AXB is equal to 1/2 of the measurements of arc B minus 1/2 the measurement of arc PU. Okay, so let's prove this. So first, since angle APB, this angle here, is an exterior angle to triangle APX, we have that angle APB is equal to angle PAX. So this is PAX here, this angle here. I'm sorry, I made a mistake. PAX should be here. PAX, angle PAX, plus angle AXB, which is this angle here. This angle here. Okay? All right. Now, angle AXB is equal to angle APB minus angle PAX. And let me call this here star. Observe that angle PAX, this is PAX, let me highlight it. And so this is the angle PAX. It is 1/2 of PU. And angle APB this angle here is can you guess? 1/2 of the measurement of arc AB, right? So by star, angle AXB must be 1/2 of AB minus 1/2 of PU as desired. This completes the proof. Okay, we'll now revisit one of the most famous results that pretty much everybody remembers from high school geometry. It states the following: if a right triangle has arms of lengths A and B and its hypotenuse has length C, then the square of the hypotenuse is the sum of the square of the other sides of the right triangle, right? There are out there there are a bunch of proofs for the Pythagorean theorems, and what I will show you today in this lecture is one very cute proof substantiating that this result is indeed true. Okay, so the main idea in proving this is to sort of cut and paste our right triangle to form this shape here. So let's start with the first triangle here, okay? And then we cut and paste it so that this now is B and this is A. So this gives us a second triangle which is congruent to the first one. Then we cut and paste this one so that now this is B and then this is A. So we get a third one congruent, and then we'll have here B and then A and so on. So this gives us, in fact, the shape doesn't look right, but this should be right here, this should be right, this should be right angle, and this should be also a right angle. So this would be then C, C, and then C. And the point now is that we are going to now compute the area of our square in too many ways. So first, A plus B squared, right, will be the area of our square. And clearly that will be A squared plus 2AB plus B squared. Okay, and we will compute the same area in a different way. Well, first we have 4 many triangles, so we have 4 times base times height over 2 plus the area inside of this square, which is C squared. So that'll be 2AB plus C squared. And these two are the same thing. So we have that A squared plus 2AB plus B squared is precisely 2AB plus C squared. Now we subtract 2AB on each side, we get that A squared plus B squared must be equal to C squared. And that gives us the Pythagorean theorem. Now we will prove the following. Given a triangle ABC, the angle at vertex C is a right angle if and only if side AB is the diameter of its circumcircle. So the first thing to note is that since the point A and the point B and C are not collinear, the circumcircle of triangle ABC does indeed exist. We have proved that earlier. All right. Now suppose we have a right triangle which is right at angle C, and we have found its circumcircle, which we know exists. And the point now is that we have to show that AB must pass through the center of our circle, of the circumcircle. Now, so angle C, we know it has to be 1/2. Let me put a point here, which I'll call V, to avoid confusion when I write down this arc. It will be half of AVB, right? Thus, the measurements of arc AVB is twice of the angle at C, but the angle C is 90 degrees, so that'll be 2 times 90 degree, which is 180 degree. Therefore, the arc AVB is 1/2 of a circle, and this is possible if and only if the chord AB is a diameter. A line is said to be tangent to a circle at a point if it meets the circle in exactly that point. So for example, if you look at this red circle here, and let's say you have the point P, we'll say that the line T is a tangent to the circle at point P. Next, the angle between a chord and the tangent at one of its endpoints is equal in degree to half its subtended arc. What does this mean? Suppose we have our circle here centered at O. We have our tangent line T, which is tangent to the circle at P. Now let's consider the angle QPT, this angle here. Okay. All right. So, well, the result says that this angle is equal to half of the measurement of, half of the measurements of the arc QP. Okay. So in other words, angle QPT is going to be 1/2 of the measurements of QP. Okay. Okay, so to substantiate the proof, we have that angle QPT is 90 degree minus angle APQ. So we take 90 degree. What is Q? QPT is the angle in yellow. So we take 90 degree and then we subtract APQ, which is what I'm about to show you in blue. So this angle here. Okay. All right. So now this will then be equal to 90 degree minus half of AQ, right? Because it subtends the arc AQ, which is equal to, well, I'm going to write 90 as 180 degree over 2. And then we can then factor 1/2 out. All right. Note that arc AQ plus arc QP is 180 degree. So AQ is this here, right? And PQ or QP is this here. So if you put them up together, you get exactly 1/2 of a circle. So that will measure 180 degree, and this means that QP is 180 degree minus AQ. Thus, angle QPT is 1/2 QP as desired. All right, now we said that two circles are mutually tangent at a point P if P is at the intersection of both circles and at the same time it belongs to one tangent line to both circles. Now, given two externally mutually tangent circles with common point P, we'll draw two common sequences AD and BC through P, and we'd like to show that AB must necessarily be parallel to CD. So first, note that BC is a transversal to the two lines AB and CD. To show the results, we only need to establish that angle B is equal to angle C as alternate interior angle. So we draw tangent ST and we'll observe that angle DPT is 1/2 of the measurements of the arc PD. Now notice that angle at C subtend the arc PD, right? So the angle at C must be then half of the measurement of arc PD, and then we can then conclude that angle at C is equal to angle DPT. Now similar arguments will show that angle at B is equal to angle APS. Since angle APS and angle DPT are opposite angles, they must be equal, and we can now conclude then that angle DCP and angle PBA are the same. Therefore, we have that line DC must be parallel to line AB. And this completes our proof as well as our lesson.